Today we're going to talk about a very powerful mathematical technique called linear algebra. And we're going to show it in the context of statistical analysis through linear models. The t-test that we described in a previous module is actually something that can be derived from the linear model machinery. So in this slide, I'm showing you a little bit of motivation. The t-test, you can think of the t-test as a corkscrew, while linear models are much more applicable. They're much more general, so you can think of it as a Swiss Army knife. So just to give you an idea of the connection between t-tests and linear models, I'm going to do a little bit of notation here. So in this picture, in this graph, I'm showing you two groups. You can see them to the left and to the right, group A and group B. And you see all these points around two means. So what is this representing? So when we were doing the t-test, we were computing the average in one group and subtracting it from the average on the other group, and that was an estimate of the population averages. Now here we're gonna write it slightly different, and later you're gonna see why we're doing this. What we're gonna do is we're gonna pick a baseline. Right? And now this average, instead of being like it was mu y before in the previous module, we're gonna call it beta 0. And then we're going to call the difference between the two groups beta 1. What is it? And now one of the nice things about this notation is that the beta 1 is really what we care about almost most of the time, is that difference. That's what we want to estimate and perform statistical tests on. So written out as a linear model, what we have is we have a group A has a mean of beta 0, and group B has a mean of beta 0 plus that difference. So we can write it like this. Now I'm doing all this because I want to eventually get to being able to write this as matrices. And the reason I want to do that is because if I write everything at matrices, everything is much easier and faster when we compute it on a computer, when we program it up. And it's also more convenient to derive mathematical properties as well. So here's how we would write the model that we're talking about. We have the average for group A is beta 0 plus 0 times beta 1, and the mean for group B is beta 0 plus 1 times beta 1. Right, so now we're going to see more on that later. So in general, the typical linear model that you will see if you look it up in Wikipedia or something, or in a book, you're going to have the observed data represented with y, and there's going to be a little subscript which is usually denoting an individual. In the case of genomics, it could be a sample. So then you have the model parameters. These are the things that we want to estimate, the things that we want to find out. In the case of men and women heights, beta 1 was the difference we were interested in. So you have a base level, beta 0, then you have these parameters beta 1, and you can have more. And then we also have these predictors or variable or covariates, is what statisticians call them, that will define the model. And in the examples that we're using up to now, they're either 0 or 1, but they could be other things as well. They could be continuous data as well. And then we usually, or almost, when we also include an error term that describes variability. And this error term could be measurement error. Like in the case of if you're measuring heights and you're doing it over and over for one person, that would be the measurement error of measuring height. But if you're taking a random sample, then this epsilon really represents the variability you get from sampling. So it's like tall people would have big errors, and short people will have very large negative errors. It's a little bit of it's not the best name when we're connecting it to biology, but it is what we call it in statistics. Okay, so now one way in which the linear model immediately becomes more useful than the t-test is in the case that we have three groups. So say that instead of men and women, we wanted to know which ethnic group is tallest. So we have three ethnic groups now instead of two genders. So in that case, we would have some baseline group, which have the beta 0, and then the other groups would be different. In what way? That we're adding beta 1 in one case and beta 2 in the other. And the nice thing about linear models is that we can write this out and in one quick computation on the computer estimate beta 1, estimate beta 2, and also get standard errors for those estimates. So here's an illustration of what we just shown. You have mean for group A, mean for group B, mean for group C. But that's not how the model is mathematically showing this. The model says this here is beta 0, this difference is beta 1, and this difference is beta 2. Right? And the nice thing again of that is that that's what we're interested in, is in those differences. So we estimate them directly. So now we're going to actually show a little bit more about matrix notation in the next module.